Hi class, today we're going over section R2, which is once again a review section. We're talking about functions and models, and we're going to be doing these 4 objectives, but mostly these objectives should all be review. You should be able to look at that and realize, yes, I know what a function is, I know how to find function values, I know how to graph a function, I know how to determine if a graph is a function, and I can graph piecewise functions. Although I know piecewise functions tend to be a little bit more of a challenge, we'll be focusing on that and also on determining function values. So we're going to be looking closely at objectives 2 and 4. First of all, let's recall that the definition of a function is a correspondence between a first set, called the domain, and a second set, called the range. This correspondence is a function if each member of the domain corresponds to exactly one member of the range. And that's an important distinction. This exactly one needs to be true. And that's each input in the domain has exactly one output in the range. Let's see a few examples. With our first example, it should be fairly obvious that each item in our domain has exactly one item in the range that it corresponds to. This is shown through the arrows. And there's only one arrow leaving each item in the domain, pointing to one item in the range. So this is a function. That's an easy function to look at. Let's look at the next question. The second example is not as straightforward as the first because we only have 3 items in our range while we have 4 items in our domain. And how is it possible that each could correspond with exactly one? And we don't look at the whole picture, we just want to look at it piece by piece and see if it actually follows what the definition says. And so we're going to look at each item in the domain and make sure that each item corresponds with only and exactly one item in the range. So the -4 corresponds with one item. The -2 corresponds exactly with one item. The 3 corresponds exactly with an item. And the 4 corresponds with exactly one item. So even though the -4 and the 4 in the domain both correspond with the 4 in the range, each of those corresponds with exactly 1. So yes, this is a function. It's not as straightforward, but yes, it's a function. For our third example, we're looking at baseball teams, and our domain is cities, and our range is teams. And what we can see is that even though Arizona has only one team, and Baltimore has only one team, Chicago has both the Cubs and the White Sox. And so that's one item in our domain having more than one item in our range. And so that correspondence means it does not have exactly one, therefore it is not a function. This is a little bit different from the example we just did. The example we just finished had 2 arrows pointing to an item in the range, which was okay because each item in the domain only had 1 arrow leaving it. But for this one, we cannot have 2 arrows leaving an item in our domain because then it's not exactly one correspondence for that item in the domain. For our last example, it's also baseball teams, and the correspondence is between teams and cities, but it's in the reverse order. We have the domain being the teams, while the range is the cities where they belong in. And you can see that each team belongs to only one city. So the Cubs belong to Chicago, the White Sox belong to Chicago, Orioles belong to Baltimore. And this correspondence is each team has exactly one city. So this is a function. Also, you must remember that whatever question is asked, you're answering that question. So it's not good enough to put a check mark and an X through these things, but you want to answer in words and make sure that the question got sufficiently answered. That's why I'm writing, yes, it's a function. The next examples ask us to determine whether or not we have a function, but it doesn't have the mapping drawn out for us. So it's asking us to do a little bit more critical thinking. And you might want to draw a mapping or maybe come up with some examples so that you can better understand what the correspondence is that is being described. The first correspondence is the page count of each book. It says the domain is the books in a library and the range is a set of positive numbers. Let's draw that out. Let's say we have a few books here in our library. And is it possible for the first book to have more than one number describing how many pages it has? It doesn't really make sense. Maybe this book has 300 pages, but I wouldn't say this book has 300 pages and it has 400 pages. So that would maybe be my only answer. And maybe this one has 250 pages, and maybe this one's 417 pages. And I'm not getting this from anywhere other than my imagination. I'm just trying to imagine what a library looks like. And when I pick up a book, is it possible for that book to have more than one set of page numbers? And when I think about it, the total amount of pages in a book is, there's only going to be one number that you're going to use to describe that. And so this looks like it's a correspondence that has exactly one answer in the range. So it looks like it's a function. So yes, that's a function. The second example asks us to find a correspondence between the first letter of a person's last name, and we're going to just go ahead and set up our domain. It says the domain is letters of the alphabet. I'm not going to put the entire alphabet here. Let's just start with the first 3 letters. And can I come up with some names in my range that will correspond with these letters? I can think of Adams. I can think of Aguirre. And already that's going to be a correspondence where this item in my domain, the A, corresponds with 2 items in my range, and therefore this cannot be a function. And so make sure you write not a function. We're moving on to objective 2, which is finding function values. The first 3 examples we have here are fairly straightforward. We're just going to replace the variable with the value in the parentheses and then simplify. So I would write f of 3 is equal to 2 times 3 plus 7, and then you simplify. And so you'd say f of 3 is 13. Using parentheses is especially necessary when we're plugging in negative numbers. So you want 2 times negative 5 plus 7. That gives us negative 10 plus 7, negative 3. So f of negative 5 is negative 3. Negative 5 is our input, and negative 3 is our output. For f of 0, get 2 times 0 plus 7, which is just 0 plus 7, which is 7. Most of these are straightforward, but our next few items we're going to plug in will be variables. Our next example replaces our variable with k, so it's a new variable that we're plugging in. So we're going to say f of k is 2, and replace the x, and 2k plus 7. It's that simple. As soon as you see whatever is in the parentheses, we replace the variable with that. The next example might look more complicated, but the exact same method. If I'm looking for f of radical k, then I'm going to take my function and replace my variable with a radical k. I have to ask myself if there's anything that I can simplify about this phrase, but I can't add the radical k to a 7, so that's as simplified as I can make it. It's actually fairly easy, right? This last one asks us to replace our variable, which is our x, with a variable phrase, which is x plus h. And so I'm going to say f of x plus h is 2 parentheses plus 7. Now that's 2x plus 7, but inside my parentheses I'm going to replace it with that variable phrase. And I can simplify this a little bit by doing distribution, but I really can't do much more than that. So I get 2x plus 2h plus 7. We're going to try this again with a quadratic equation next time. For question number 4, the difference here is that I actually have x twice in my function. So whenever I plug something in, I'm going to have to plug it into both instances of x. So take care to do that well. Our first question is k of 0. So k of 0 will be 2 times 0 squared plus 5 times 0 minus 7. And that's just 0 plus 0 minus 7. So you get negative 7. The next question asks us to evaluate k of negative 3. And it's a negative number. Make sure that you put it in parentheses. And you're going to plug it in twice. And you have to remember some things like parentheses before, or exponents before multiplication. So I'm going to say that's 2 times 9, because negative 3 squared is 9. I can do this multiplication here. Get 18 minus 15 minus 7, so I get negative 4. So k of negative 3 is negative 4. This last term that we're going to be plugging in actually is 2 terms, and so we have to make sure we are very careful about doing that. When you plug in x plus h, especially into a square, you have to make sure that you know how to multiply that correctly. And that is a perfect square. That becomes x squared plus 2xh plus h squared plus 5x plus 5h minus 7. And that becomes 2x squared plus 4xh plus 2h squared plus 5x plus 5h minus 7. And when I look at this, there's actually nothing here that I can simplify. None of those terms are redundant. Let's just write it once for clarity. K of x plus h is 2x squared plus 4xh plus 2h squared plus 5x plus 5h minus 7. It's a long phrase, but that's what we get when we substitute in x plus h for our variable. Let's evaluate f of negative 4. So, plugging that in, I get 5 times negative 4 minus 3 times negative 4 squared. So that becomes negative 20 minus 3 times positive 16. Remember that negative 4 squared needs to happen before you multiply the 3 and the 4. And then we get negative 20 minus 48. So that's negative 68. Plugging in x plus h, we have to remember to plug it into both x's. I'm going to get 5 times x plus h minus 3 times x plus h squared. And recall that the first one we could have multiplied out, but the second one we do want to do the square first before we multiply times the negative 3. And the square of x plus h is not just x squared plus h squared, but it's x squared plus 2xh plus h squared. So you have to take care to do that properly. And then multiplying this out, we have to distribute that negative 3 to all the terms. And we look at this, and the reality is that none of these terms can combine, so we're done. This last portion asks us to do several things. It's actually called the difference quotient, and this difference quotient is something that we're going to be doing several times in calculus. So this is an important thing to be able to do. Notice that we already found f of x plus h here in green, And we already know f of x here in blue, so we're going to refer to our previous answers when filling in this fraction. But basically I'm going to get 5x plus 5h minus 3x squared minus 6xh minus 3h squared. And we're going to put that in parentheses, and then we're going to subtract our original function, 5x minus 3x squared. And it's really important that you put both functions in parentheses, and then you put that over h. Why it's important is because there's a subtraction between these functions, and when you have multiple terms, you want to make sure that you do that properly. So we're going to have to distribute that subtraction. Let's simplify this once. And then you get plus 3x squared. Make sure you change that sign when you distribute it. And then we're going to see if we can, through addition or subtraction, cancel out any terms. So I see the 5x and the negative 5x. I'm going to cancel those out. And then I see a negative 3x squared and a positive 3x squared. I'm going to cancel those out. And then I'm going to rewrite what I have as 5h minus 6xh minus 3h squared over h. And let's factor an h out of that numerator. I would be left with 5 minus 6x minus 3h all over h. And then let's go ahead and reduce that fraction because I have a term on the numerator and denominator that can cancel out. And so I'm left with 5 minus 6x minus 3h. I want to point out that on the second step, right around here, we canceled out through addition and subtraction. But on this step over here, we canceled out through division, and you have to factor. You have to factor that h out of all the terms in the numerator and make sure that when you do that division, you do it properly so that you can get the correct answer, 5 minus 6x minus 3h. The vertical line test helps us look at graphs and helps us determine if it's a function or not. We're on objective 3, and so just by looking at the graph, whether or not we know what the inputs or outputs are through a mapping or through a function, we can look at this graph and we can say, hey, you know what? If I drew a vertical line through it, that vertical line will intersect it at most one value of y for each value of x. So for each vertical line that I draw, it will intersect it only once. So yes, that is a function. But when we look at b, and I draw a vertical line here, that's going to intersect that graph 2 places. And so that's 2 values of y for the one input of x. So that's not a function. The same thing with c. I can draw a line here, and it will intersect it twice. So it's not a function. But when I look at d, if I draw a vertical line, anywhere where I draw a vertical line will intersect that graph only once. And so that is a function. So that vertical line test is a quick, easy, visual way to see if there's more than one output for any given input. We're moving on to example 7, and we're doing piecewise functions now. And the idea behind piecewise functions is that it's a function that's defined differently in different regions of your domain. So we look at the right-hand side and we're going to delineate our domain at -1 and at 2. The very first thing you should do is divide your graph into regions according to the domain on the x values. So I'm going to draw a line, a vertical line at -1 and at 2. Now if I look at this first domain, it says for x values that are less than or equal to -1, that is this region right over here. And so I'm going to be graphing this function, which is just the value of 2, on that domain. So I graph 2 on that domain, and on the endpoint, I am going to put 1 over 2. a choice between an open circle and a closed circle. Well, notice that it says for values that are less than or equal to -1. And so if it's equal to -1, I'm going to put it at 2. So I'm going to make it a closed circle right here. Another way to think about this is by plugging in numbers that are in this domain. So plugging in -3, -2, -1. And when I plug it into this green function, I should get 2 each time, because that's the answer. So that should make sense why we graphed that. Let's go on to the middle region. This middle region is defined by the domain x is between -1 and +2. That's this pink region right here in the middle. So that's where I'm going to be graphing. Now, let's plug in the numbers. And when I plug these numbers in, I will get -3, -2, and +1. I'll get -3, -2, and +1. Now the thing is, if I were to try to plug this in, I would get -2 over here, but I don't really, because when I plug in -1, I get that 2. So we're going to put an open circle here and a closed circle here. We're going to graph this portion of our parabola. And moving on to the third region, it says for our domain where my values of x are greater than 2. And so that's our third region right here. So plugging in 3, 4, and 5 into this blue function, I will get -2, -1, and 0. I get -2, -1, and 0. If I were to continue that line in both directions, that would end up here, but I can't have a closed circle here. So why can't I have a closed circle there in blue? Because the value when I plug into the function is +1 over here. And I can't have it have both +1 and -3, otherwise it wouldn't be a function. So one of these circles has to be closed, and one of them has to be open. Before we consider ourselves done, we do have to label our graph, otherwise it's just a bunch of lines with no values attached to them. And I consider it important to put values anywhere where there's a point. You don't have to do it the entire graph, but you do have to label it enough that I know where you put your lines at. Hopefully the color coding is helping you understand where each of these need to go. Remember, our first step was dividing up our region into regions defined by the values here, which tell us what our domains are. And it helps me to color code, and that way I know if a number is within that region, then I'm going to plug it into just that first function. And so you want to make sure if I'm plugging numbers 0, 1, and 2 in, those are with the pink function, I'm only going to plug them into here. And so hopefully using those colors helps it make it more clear for you to graph. The inequalities in this piecewise function are a little bit different than the ones we had last time. We had greater than and less than symbols last time. Now I have equal to and not equal to. But that's still going to delineate our regions for us. We have when x is equal to -2 a function, and then when x is not equal to -2 a different function. Let's go ahead and put -2 in on our x values. So that's going to delineate between our two functions. One function is on the line, the other function is not on that line. Let's go ahead and do the regions where x is not equal to -2. That's the second function on our list. And so that function is x plus 3. So -4 plus 3 is -1. -3 plus 3 is 0. -1 plus 3 is 2. 0 plus 3 is 3. 1 plus 3 is 4. And let's plot those points. -4 is -1. Then we have 0. Then you have -1, 2, 0, 3, and 4. Now, we're going to be drawing that and connecting them to make a line. And we know that that would be a line everywhere else. What happens right here on that dashed line? We're going to put an open circle, because on that dashed line it does not have that value of +1. What value does it have? Well, at g of -2, we're going to go with our first domain, and so we're going to go with that first function, which says 4. Then we're going to put the value at 4. Let's put it in blue. And so you can see this piecewise function is a line that's consistent everywhere except for one spot where it jumps to a different value and then it jumps back to that line. Let's label our graph. You want to make sure it's labeled enough that you can know where all of your points are. You want to make it clear that there is an open circle right there where that blue line hits the dash line, and that that value is actually at 4 and not at 1. So make sure your graphs are clear. Make sure that you're looking at each portion of the graph and you're looking at that domain, making sure that each answer is in accordance with a function related to that domain. Thank you. That's it for the section. Have a good day.